In this video, we're going to discuss additional Reimann sum applications. In Calculus 1 or Math 140 at Penn State, we introduce the Reimann sum to approximate area of some region under some graph. Then with the Reimann sum, we can introduce definite integral. So before we see additional Reimann sum applications, I want to review what was done with the Reimann sum and how it was done. Given a function of x, suppose this is the graph. We consider the graph of f of x over interval a to b on x-axis. Now, under the graph of f of x and above the interval a to b, this is a region that we are investigating. We want to find the area of this region. Well, because the top is not straight, there's no existing area formula that we can use to evaluate area of this region. So in Math 140 or Calculus 1, we learn to slice the region into many strips. For example, say this is one of the strips a representative would pick up among many. Usually what we do for practical reason is to slice the region or interval evenly into n parts. Say this is one part with width called delta x. Sometimes we use a dx. Delta x, x increment, dx, x increment, the same thing. So idea is, if we can somehow figure out the area of one strip and then add areas of all the strips up, and that would give us area of the whole region. Okay, let's start with this one strip. Let me enlarge the strip and put on the side so you can see better. So this is the one strip with the width dx or delta x. Now still, because the top generally is not straight, there's no formula. So before, what we did was to evaluate the function. This is a part of a graph of function. Evaluate the function at some point within this interval. For example, evaluate the function at the right endpoint, denoted as x of I. So we have f of x of I, and then use the height of the point here, which is the value f of x, to construct a rectangle. Now, for the approximation to be accurate, we usually slice the interval a to b into many strips. So practically this width is a very small, very narrow strip. So because it's so narrow, practically the area of rectangle constructed this way is very close to the area of the actual strip with curved top. So we said area of the strip is approximately equal to dA represents area of the actual strip. So area of the actual strip is approximately equal to area of such green rectangle, the height times the width. They're not exactly the same. There's some error which we accept. So anyway, this product would be approximately the area of this strip. Now there are n strips because we divide into n parts. So the total area would be approximately equal to the sum of these products, I from 1 to n. And this sum is what we call the Reimann sum. This is one type of a Reimann sum. Now there are many different types. It depends on where we pick up the point to try to come up with the height for a rectangle to be constructed. Usually we pick up, like I said, the right end point because it's very easy to come up with a formula. So this will be actual formula for the each right end point. It's easy to understand too. The total length is b minus a. If it's divided into evenly n parts, each part would be b minus a over n. Now you start from a. So the first point where you slice the region would be b minus a over n added to a here, and this will be second point will be two of those added to a, so on. Anyway, if we use the right end point, this formula is called the right end point approximation, right end point the Reimann sum approximation. We could choose, for example, other cases, middle point. Within each strip we choose a middle point called mi. Mi middle point from each strip. We would have a middle point approximation. In general, mathematically, we could pick up actually any point, some arbitrary point, just anywhere. That's still called the Reimann sum. They're all called Reimann sum, but this is more general. Those two are more common. specific locations, right endpoint, middle point. It could be just any point. It can be shown mathematically under some condition when delta x is very, very small. In other words, we slice the interval a to b into many strips. They're all small. Then doesn't matter which way you do it, the arrow is all very small. So any of those Reimann Sum approximation can be good, can be useful. In other words, there's not much difference how you construct the Reimann sum. As a matter of fact, whether you use a right endpoint to create a Reimann sum, or middle point, or any arbitrary point within each subinterval, when n is very, very large, say n goes to infinity. Now mathematically what it means is we would send n to infinity. So practically it's like saying we're slicing this interval into infinitely many parts. Then there's no difference at all. They will all represent the actual area of the region. So if we send n to infinity with any of those guys, but normally we use this one because there's a very convenient formula for their locations, x of i's. So let's just pick up this one. I from 1 to n goes to infinity, of course the x of I, just copying down, will be a plus I times b minus a. So the limit of any of this Reimann sum will become exact area of the region. So this is how we use Reimann sum to try to calculate the area of region under a graph of some function. Now, for specific problem, we'll be given the function and the interval. So first we would, determine the x of i's using this formula. Then evaluate the function at each x of I and multiply by the width. Of course, if it's done evenly, this part dx would be b minus a over n. So we can construct Reimann sum. It's a summation. So we simplify it, then we evaluate the limit and find the area. It's a lot of work. Now, this whole process is based on the idea of a slicing region. So let me try to recapture the principle, the idea involved. The function, same f of x over interval, and so there has a region under a graph about interval a to b. We want to find its area. Now, what was done was the region was sliced into many strips, and we try to figure out the area of each strip and add them up and send into infinity. That's to divide the interval ring into infinitely many parts. So we try to do the same thing here. So slice into infinitely many parts and pick up a part, pick up a strip. The width is dx, the height. Now, of course, from our description, we could pick up any point within the interval and evaluate the function. So it's so skinny, we can just say pick up x. X can move, anywhere within the strip. So arbitrary location, and evaluate called f of x. Therefore, the area of the strip is approximately f of x dx. So it's like a height times the width. Product would give us the area. Then we would add those up. We will start from the first strip, start from A and all the way to B. Therefore, we just kind of add kind of an A to B, that kind of thing. A to B, f of x dx. Now this is summation. We actually then use a stretched s, not a sigma. Sigma, it's what we use in summation notation. We try to come up with a new notation to represent the whole process. We say A to B. So we invented this new mathematical expression to represent the whole process. So this is really what we were doing before. The product here is basically this part, and the summation symbol we call integral sign. Integral sign represents the sum from 1 to n to n goes to infinity. In other words, it's like 1 to infinity, or practically it's like adding from end A to end B. So this is really how we come up with this expression to denote the area approximation, area computation process. So let me copy the notation. It's called integral expression. What it is really this limit expression we come up with when trying to use Reimann sum to evaluate area of the region, like this. So this is what was done in calculus 1. We use Reimann sum to try to evaluate area of the region with limited expression we called integration. The integration was introduced. Then we discuss, of course, simple formulas, properties of integrals like this. And also we learned how to evaluate this kind of mathematical expression we called definite integral. Now, before we see additional Reimann sum approximations in different situations, we want to see some examples how we try to evaluate really value of such limit by evaluating the equivalent integral expression. Okay, here is well, a Riemann sum involving mi. That's midpoint. After that, we try to evaluate limit. So to find the value of this limited expression, we will not actually set up the Riemann sum, simplified, do the limit. Instead, we'll try to use this integral expression to do it. So we're going to find the value of this by evaluating an equivalent integral, definite integral. Well, how do we do it? Let's put this right underneath. What we'll do is to turn the limit summation to integral, and this is the function, this is the delta x or dx. So according to the formula here, this limit expression becomes integration, that's this part, a to b, 0 to 4. This is a function. So we turn the point, middle point, to just some arbitrary point x, square root of x squared plus 9 dx, according to definition of definite integral. So this is the first part. We turn limit to definite integral, then evaluate. Well, we learned in calculus 1 how to evaluate the definite integral. First, we find the antiderivative, then we plug in upper limit, plug in lower limit. So let me find the antiderivative on the side first. For this, we would do a substitution, like a u equal to x squared plus 9, du equal to derivative of that is 2x dx. So the expression, the radical expression, becomes the square root of u, because x squared plus 9 is what we call the u now. And the x and the dx together, according to this, is 1/2 du. So this is called the substitution technique. Now pour out the half. This is just power we integrate. Then we use power formula. Integral power is 1 over the power plus 1 u power plus 1. Let me simplify. 1 over 2 plus 1 is 3 over 2, so flip is 2 over 3. And then the u, we're done integration, so bring x squared plus 9 back for u. Power is 3/2. And we're doing definite integrals, there's no need to have the constant of integration, which would get cancel out anyway, so don't need the plus c. Now this is the antiderivative. So here let's continue with our evaluation of definite integral. With the antiderivative, well, we're going to, let me just write down first. So 2 cross out, it's 1/3. So the antiderivative is 1/3 x squared plus 9, 3 over 2, then 4 upper limit, 0 lower limit. Just plug in. So it's 1/3, 4 plug in, 4 squared plus 9, 3 over 2, minus 0 squared plus 9. Now this is the order. We plug in upper limit for x first, lower limit the back, and then simplify. 16, 9, 25. Zero 9 is 9. So we have 25 again 1/3 power first, one half power square root is 5, so it's a 5 to the third power minus 3 to the third power. Again, I'm taking square root, which is a half power of 9 first. So this is, well, we can pull out 1/3. 5, 5, 25, 125 minus 27. Well, just it's going to be, what is that? 98. Yes. Yeah. Well, so it's 98 over 3, whatever. But anyway, so this is how we try to find the value of limit of Riemann sum by evaluating equivalent definite integral. Because of this definition. Let's just quickly see another one, just to go through the process. So again, the key is we start with the limit of Riemann sum this time, x of I star. So x of I star could be any point from each subinterval. It doesn't matter. The limit summation becomes integration. Again, limit summation becomes integration, and the f is this part. This is function. That's 3x squared minus 1. Doesn't matter you have middle point, right end point, or arbitrary point. They all turn to x. Just x. In dx, now we can go from -1 to 3. Okay, so this is the first step. Turning limit expression, limit of Riemann sum to definite integral expression. We found the antiderivative. This one is really simple. It's just x to the third power minus x. Then plug in the upper limit for x, plug in the lower limit for x, and simplify. Yeah, 27 minus 3 minus -1 plus 1. That's 0, cancel each other, so it's 24. Now, before we see additional Reimann sum approximations, I want to comment on this new expression we called definite integral. Of course, we start out with the area computation. Created Reimann sum, take a limit, then we call it as a definite integral. But now this can be just a pure mathematical problem. As long as the function is given, whether it's about area or not, given function over interval, we can always set this up, so we can always do the definite integral. So this can be just some mathematical work we do. It may not necessarily represent any area or what. Okay, let's see additional application of Reimann sum. One application of Reimann sum is involved in total mass computation. Let's say there is a thin rod that occupies interval A to B. And number 9. Suppose we know the mass, density of mass distribution. So rho of x represents density of mass. What it means is it's a mass per unit length across the interval. It's not constant. In other words, the mass at this end may not be the same as mass at say this location. Varies from point to point. Well, since the density is not a constant, so we cannot directly calculate total mass. But what would be the total mass of this entire rod? Well, we're going to slice the rod into many sections. Say here's one section that has width dx or length dx. Let me enlarge it. Let it pour out and then enlarge it. So the width here is dx. The same idea applies here. What we try to do is to find hopefully mass of this short section and add them up. Now we start out by slicing the rod into n parts again. So each part, the mass is approximately the density evaluated at any point across this length and times the length. Well, how can we do this? It's because we assume this section is very short. Therefore, although the density still varies from point to point, it's not going to change much because it's so short. The function is not going to change much. We can consider the density across this short section to be approximately the same as this density function evaluated at any point. For example, at the right end point, at the middle point, or any point at all. So just say rho x. Just call it rho x. So the density across this section is all the same, multiplied by the length of this short section. That would give us approximately the mass of this short section. Then we add them up. There are n of them. Well, the whole rod is sliced into n sections. Then we send n to infinity. So here again, this is like a Reimann sum. Same Reimann sum as we established for area approximation. We send the n to infinity. Mathematical theory goes that this would give us the exact mass. Now mathematically, this is the same as a definite integral we introduced earlier on, because this is the same kind of Reimann sum, and then the n goes to infinity. Such mathematical expression is called a definite integral. So in this example, we try to find the total mass of a rod which has varied density distribution across the rod. We apply the same Reimann sum idea and end up with the same kind of a mathematical work. the definite interval. Now let's see one example. Suppose density distribution function is 60 minus 2x from 0 to 10. So this end is 0, this end is 10. We're not going to go through the slicing, small section, or whatever details here. We'll just go right to the end result, because this will lead us always to the same exact definite interval expression. Therefore, the total mass, according to our discussion, will be again just a definite interval 0 to 10. Density dx. Now it's just a matter of evaluating this very simple definite interval. Find the antiderivative, 60x. Find the antiderivative, that's x squared. Plug in 10, plug in 0. So 10 plug in, 60 times 10, 10 squared minus 0 minus 0, 0 for x, 0 everywhere. This is 600 minus 100, or 500. So this is another example of how we try to establish Riemann sum to calculate the total mass. We end up with a definite interval again. Next, we want to see in physics. Suppose in physics we try to figure out the distance traveled. Given an interval, time interval, a to b. Suppose we know the velocity function v of t of a moving object. Now we want to find the distance traveled from time a to time b. Well, velocity is not constant. It's different from time to time. It's impossible to directly calculate distance traveled. Not the same as when distance is constant. When the velocity is a constant function. For example, always 60 miles per hour. If the velocity is constant, we simply multiply the velocity by time traveled, like 2 hours. Well, if it's 60 miles per hour constant, right? 2 hours, 120 miles, just multiply. But when the velocity is not constant, we cannot directly multiply. We know the time interval, a to b, so it's b minus a. That would be the total time. But since this is not a constant function, cannot multiply. Well, how we do it is again to slice the time interval into many parts, eventually infinite many parts. But we start with the n. Pick up a section of this time interval, sliced or cut this way. Suppose, let me just say, this is a short time interval, length dt. Within this short time interval, it's so short, we kind of treat the velocity to be a constant. It doesn't matter what moment you try to evaluate the velocity, it's not going to be much different For this reason, we can evaluate the velocity at the right endpoint of this time interval, or middle point, or any point, or generally say v of t. Pretty much all the same across this short time interval. Therefore, the distance traveled within this short interval will be vt times dt. Then we add 1 to n, we send n to infinity. This becomes a limit of a Reimann sum. Well, this is what we call definite interval. So this definite interval would give us the total let me not say total distance, let me just say distance traveled from time A to time B. Alright. This definite interval would represent the distance. But actually there are two types of distances we are interested in physics. This distance will give us what's called the net distance. What it means is, when we try to do this, velocity function, well, could be positive, could be negative. When velocity is positive, we're adding the distance going forward. When velocity is negative, it's going backwards. So it's actually subtracting some of the distance already traveled. In physics, this is called the net distance from moment A to moment B, the actual change in location, the distance between the locations. There's another concept in physics we're interested in. That's when we try to set up the Reimann sum. We make velocity positive all the time. What it does is to ensure that all the distances added up are added up. There's no cancellation. They're all positive. For example, within this time interval going forward, next forward, suppose then next backwards, so it would be negative. It would be subtraction, but we, with the absolute sign, we make it all positive. In other words, all added up, all the distance traveled added up. In reality, this would give us the mileage, the total mileage traveled. So we would still do a Reimann sum. This is still Reimann sum. It's just that we turn every term to be positive. 1 to n, n to infinity. This is still definite interval. A to B this time is absolute value of velocity. We integrate. This is called total distance. Total distance is like a mileage traveled, where net distance is the actual change in location. We have this because the velocity could be negative. Alright, now so this is how we try to determine different type of distance traveled using the Reimann sum. In physics, we end up with really just two definite interval. This one is just like before, just giving a velocity function, just integrate from A to B to get the net distance. Total distance or mileage, similar. The difference is that you have to take absolute value first. So next I'm going to show you how to actually evaluate definite integral of an absolute value function. Suppose velocity is 40 minus 24 over interval 0 to 10, t from 0 to 10. Now let's go right to the mileage formula. Total mileage, total distance, 0 to 10. Absolute value of 4t minus 24. Setting up the integral is pretty simple. It's just apply the formula. What I really want to show you is how we sometimes try to evaluate definite integral when there's absolute value signs. There's no integration formula for function with absolute value signs. Well, I'm going to show you how to do it in this example. Like I said, there's no formula, so first we have to get rid of absolute value signs. So we call absolute value expression. Absolute value of anything equals a. If we know a is positive, it be negative a if we know a is negative. So the key is to determine the sign of the thing inside absolute value signs. For this, we need to construct a sign chart 0 to 10. We want to determine where 40 minus 24, like our capital A, we want to determine where this thing is positive, where this thing is negative over interval 0 to 10. Algebraically, we first find where it's 0. So we set it to 0 and solve for t. Now this is simple work. 24 move over t equal to 6, easy enough. Now we know at 6 there's only one solution, 6, so we know only at 6 well 40 minus 24 will be 0. It's not going to be 0 elsewhere. In algebra, because of this, we know in algebra from 0 to 6 the function will be either completely positive or completely negative. From 6 to 10, again, it's going to be entirely positive or entirely negative because there's no 0. For the sign to change, there has to be 0. This can be seen from graph 2. See, this graph is positive and change it to negative because, well, it actually crosses 0. This function negative change to positive because it crossed 0. So if there's no 0, it's not going to change the sign. That's really what it is. Alright, so we find the only location where 40 minus 24 is 0. Now just test out those two intervals, 0 to 6, 6 to 10. See whether this is going to be positive here or negative here. Also here. So pick up just any point to test out. Pick up 1. 1 plug in, 4 times 1 is 4 minus 24 is negative. So we know at 1 the function is negative, and we're sure it's negative entirely over this interval. Similarly, 6 to 10, we know the sign is not going to change because there's no 0. Fine, there's only one location where function is 0. So we know it's not going to change sign. We just have to know whether it's going to stay all positive or negative. Pick up, say 9 to test out. 9 plug in for t. 4 times 9, 36. 36 minus 24, positive. So we know it's entirely positive here. Alright, now the sign chart is going to help us determine how to get rid of the absolute value signs in the integral. Well, first, because the sign is different from interval to interval, so we need to split the integral into two. 1, 0 to 6. And 6 to 10. the absolute value expression will be treated differently over different sections. Okay, start with the 0 to 6. Well, from our sign chart we see 40 minus 24 is going to be all negative. Therefore, based on the definition of absolute value expression, we can get rid of the sign, absolute value signs, by placing a negative sign in front of the expression. So we can do negative 40 minus 24 without absolute value signs. Over interval 6 to 10, now this interval, over this interval, we find out 40 minus 24 stays positive all the time. In other words, this is positive, then there's no need for absolute value signs. That's what this says. It says the A itself is positive, you can just get the A out. Just get rid of the absolute value signs. That's what we did for the second interval. So now we have two definite intervals, just normal, without absolute value signs. Just find the antiderivative each, just plug in upper limit, lower limit. This one, it's antiderivative is 2t minus 24t 6 0. The second one, it's 2t squared minus 24t 10 plug in 6 plug in. The rest is just straightforward computation. For example, the first one, you plug in 6, you get 2 times 6 squared minus 24 times 6. The 0 plug in, you get just 0. The second one is more complicated. You have plug in 10, 2 times 10 squared minus 24 times 10 minus, there's 6 plug in, that's not 0 this time. It's 2 times 6 squared minus 24 times 6. Now with the calculator, and well, let's see what we get without the calculator first. 6 squared is 36, so it's 72. 24 times 6, use calculator. 24 times 6, 144. And this is 72 again. 36 times 2. 24 times 6. Wait, I missed a lot. Okay, let's see. Okay, alright, let's do this. So this part is this. This part is that. Let's get it this first. There's this guy actually. I didn't do it, so let's see. It's 100, so it's 200 minus 24, 240. Anyway, so again with the calculator, just negative together is negative 144. There's a negative positive negative positive is twice 144, and this is negative 40. Now we have, well, 144, 144, two of them, one of them says 144 minus 40, 104. Alright, well, through this example, I really just wanted to show you how to evaluate a definite goal involving absolute value signs. The key is to know the sign of this guy, 40 minus 24, the velocity function over the interval. Simple algebra. You find where it's 0 first, then check the the sign over each subinterval, so you know what to do with the absolute value signs, whether you can just throw it away or you throw away and put a negative sign in the front. That's all it takes. From this point on, it's just a standard trivial integration. Find antiderivative, then plug in upper limit, plug in lower limit, and simplify. Alright, so this is what we want to discuss in this video. Is some more application of Reimann sum. Before, we learned to use Reimann sum to do area computation, and now we learn we can do total mass. We can try to figure out distance traveled when velocity function is given, total distance or net distance. Net distance, of course, is much easier. You don't need to worry about the absolute value sign at all. You just directly evaluate a very simple definite integral when the velocity function is given, time interval is given. Okay.